சொல்லியிருப்பாங்க மேம் மணி ஆறா போய் அது தெரியல சொல்லு. This is week 12 of the thermodynamics course. Previous week we saw reactions in chemicals, how to solve those. We did component balances of each component, or as per se mass balance, and we do the energy balance to solve the problem. This week what we will see is chemical and phase equilibrium. So any reaction, uh, the reactants and products come to an equilibrium. Uh, so how to solve that? When the previous week what we solved is when we say that the whole equilibrium is completed and the products is formed. In actual case, that may be different. You may get some intermediate products and so on. So how do we find that? So in previous case, that's why we did a dry analysis in the problems. We saw that there was a dry analysis and we saw the components and each of the fractions was given. So to estimate that, we use the concept of chemical equilibrium. So equilibrium is the state where in terms of chemicals, so if you say hydrogen and oxygen is reacting to form water, then at a certain point of time you will have hydrogen oxygen which is forming water, and water is also dissociating into forming hydrogen oxygen. So there comes a point where there is no further reaction again that will change the composition of the components present. So at that point you can say it has reached an equilibrium. So how do we estimate that? So equilibrium is always goes towards any thing to a least energy state. That's where your system proceeds, or as per the second law, where the entropy is maximum. So for a given conditions of u and v, so internal energy and volume, if you are keeping it constant, then you will see that you have to maximize the entropy, and that gives you your equilibrium. But normally what we encounter is your pressure and temperature, fixed pressure and temperature. When you have a fixed pressure and temperature, you say that your energy for any reaction to proceed or to go, it should go towards a minimum energy state. So for a given pressure and temperature, when you are having fixed temperature and pressure, so at that point you say that your Gibbs energy should be minimum for the given variables pressure and temperature. Your Gibbs energy will be minimum. So your reaction or your phases in equilibrium, everything proceeds towards this minimum Gibbs energy state. So easier example, if you see this is a chemical reaction which you saw, say hydrogen and oxygen forming water. So this composition at the end, which what composition of hydrogen, oxygen and water is present, it depends upon this chemical equilibrium. So an example of a phase equilibrium, if you see, is we see multiple examples in your day-to-day life. So if you are mixing Horlicks with your milk, so that is an example. So if you see that both your different phases, but when you mix it forms a single phase. So that mixture is at a lower Gibbs energy compared to your separate. Another example is your oil and water. So they don't mix. So their mixed Gibbs energy is more compared to your separate. That's why you have two phases of oil and water don't mix. So they separate out. This because this separated Gibbs energy is lower compared to the mixed Gibbs energy. So this is an example of phase equilibrium, and in anything to exist in equilibrium phase, you have your chemical potential will be equal in each of the phases. So with that note, we will see how to solve this chemical equilibrium problems. So for that, we'll use a concept called to find out the K value, which is defined as when you this all comes from the Gibbs energy and equating the chemical potential. So your K will be equal to your in terms of pressure and your mole fractions. So mole fraction raised to the individual coefficient of the reaction, and of the products divided by the reactant into your pressure, P by P reference raised to power your difference in the coefficients of the products minus reactant. So that's what you will get. So with those we can estimate the chemical equilibrium composition, and this K values you can get it from any book they would have given at for a given mixture. So we'll see how to solve this. So moving on, the first problem is we have 1 kilomole of CO2 at 1 atmosphere and 2700 Kelvin, which decomposes to form an equilibrium mixture of carbon dioxide, carbon monoxide and oxygen. So determine the composition of the mixture. So first at equilibrium we assume that we have x kilomoles of CO2. So CO2 is decomposing into CO2 plus CO and O2. So we assume some x amount of CO2 is present at after dissociation. So we do an balance to find out what is the composition for oxygen and carbon monoxide. So if you do a carbon balance here, so you have x moles of CO2, so you have 1 mole of carbon dioxide initially, so you'll have 1 minus x moles of carbon in carbon monoxide. So carbon monoxide is 1 minus x. So similarly you can find out for O2. We're doing an oxygen balance, so it will come out to be 1 minus x by 2. So this is the reaction which we get. So now we need to find out the x to estimate each of the composition of component. So initially if you see, we have CO2 as 1 kilomole and carbon monoxide is 0 and 0. So at equilibrium we have x kilomoles of CO2, 1 minus x kilomoles of CO and 1 minus x by 2 kilomoles of oxygen. So if you add this up, we will get 3 minus x by 2. So that is the total number of moles which is present. So dividing by that we can find out the mole fraction. So x by total moles, so x by 3 minus x by 2. So this is what I get, 2x by 3 minus x, that's what is the mole fraction for CO2. And similarly you can estimate for carbon monoxide and oxygen. And again if you add this up all, you will get 1. So that's what you should get, the mole fraction, summation of mole fraction of all the components will give you 1. So now to find out the final composition, so the reaction how the CO2 proceeds is, CO2 is decomposing into CO plus half O2. So this is the reaction, and this is the chemical equilibrium which we have specified. So the reaction is CO2 decomposing into CO and half O2. So this is forward and backward signs, this shows that it has reached equilibrium. So CO2 is in equilibrium with CO and half O2. So from a table for this reaction, we can estimate at 2700 Kelvin, your K value is, log 10 K value is minus 1.0094. So from this we can find out K. K is nothing but log 10, so you can take to 10 to the power of the value to find out K. So K is 10 power minus 1.0094. So this is equal to the K expression, which is the mole fraction of individual component raised to power the coefficient in the reaction, divide by your product into your P by P reference raised to power your difference between the coefficients of the reactants minus products. So in this case, your reference temperature you are assuming it to be same as the reaction, so 1 atmosphere. So that term goes away. So your K value is nothing but your component mole fraction raised to power the coefficient divided by the product reactant raised to power the coefficient. So your product is CO and half O2 and your reactant is CO2. So K is equals to mole fraction of CO and your coefficient is 1, and into mole fraction of oxygen. Here your coefficient is half, so mole fraction raised to power half divided by your mole fraction of CO2. So here we have already found out the mole fractions of each of the components. So substituting that, we'll get 1 minus x by x raised to into square root of 1 minus x by 3 minus x. So this is the reaction equation which will get substituting the mole fraction. So here if you see, the only unknown is x. So if we solve for x here, we'll get x as 0.7674. So we have found out x now. So when you go back again and substitute the mole fraction expression, and also in moles, you can get in moles. Substituting that, you can find out what is the individual moles of the components present, and also the mole fractions of each of the components. So substituting x equal to 0.7674, it will give you CO2 as 0.7674 kilomoles of CO2, 0.2326 kilomoles of CO, and 0.1163 kilomoles of oxygen. So if you add up, you will get 1 kilomole. So initially your carbon dioxide was 1 kilomole, and if you see after reaction, you have 0.7674 kilomoles of CO2. So that means you have close to 25% of CO2 which has dissociated. So moving on to the next problem, we have carbon monoxide at 298 Kelvin enters a reactor that is operating at 1 atmosphere. It is burnt with a stoichiometric amount of air that enters at 298 Kelvin. So you have carbon monoxide which is coming into the reactor, and you are supplying stoichiometric amount of air with the same temperature. The product of the combustion leaves the reactor as an equilibrium mixture of carbon dioxide, CO, and O2. So your initial, it's the other way around. Previously we saw is carbon dioxide dissociating into carbon monoxide and oxygen. Here the carbon monoxide is reacting with oxygen to form CO2. So now determine the composition of the products at the rate and the rate of heat removal from the reactor. Assume steady state operation. The nitrogen in the air may be assumed to be inert. So now like similar, we assume that we are having x kilomoles of CO2. So you can assume any component as x, but here we are assuming x kilomoles of CO2. So if you see, your reactance is, you have CO which is reacting with stoichiometric amount of air. So half O2. So you have half O2 because to form CO2 you will require, if you are using 1 moles of CO, you require half moles of oxygen to form 1 mole kilomoles of CO2. So that's why half. So if you take that, this is stoichiometric amount of air. So CO plus half moles into air is containing oxygen and nitrogen. So oxygen is O2 plus 3.76 moles of nitrogen. This reaction gives you, we are assuming that at equilibrium you have x kilomoles of carbon dioxide. So x CO2 plus, again if you do a carbon balance, you will get 1 minus x CO plus 1 minus x by 2 O2. So this is similar to what we got in the previous previous problem expression. So then here nitrogen will have the same amount of nitrogen here. So 1.88 N2. So now we know each of the species how many moles are present. So if you see initial moles, so there is no CO2, so that is a product which is formed. Then CO, if you see, we are assuming 1 kilomole, so 1 kilomole of CO. So it is reacting with half kilomoles of oxygen, so 0.5, and the nitrogen present is 3.76 into half kilomole air. So half into 3.76 gives you 1.88. So next is we are assuming at equilibrium we have x kilomoles of carbon dioxide. so x, then CO is 1 minus x, and oxygen is 1 minus x by 2, and nitrogen is 1.88. So now similarly we can add this all up, we will get the total number of moles is 6.76 minus x divided by 2. So now we can divide this with each of the moles, component moles. So to find out mole fraction, so that will give you CO2 as 2x divided by 6.76 minus x, and similarly for rest of it. So and if you add up, you again see that you will have your summation is 1. So this you can use it to make sure that what you did is correct, what you found out the mole fractions are correct. So you can always use that summation of any fraction, mole fraction, mass fraction, any fraction, it will sum up to 1. So now we see the reaction is determined by the same reaction. CO2 is in equilibrium with CO plus half O2. So it can be either way. At equilibrium, CO2 dissociates into forming CO plus half O2, and same amount of CO plus half O2 forms CO2. So that's why the composition doesn't change. So you can express the same expression. So for this, at 2000 Kelvin, we will find out the K value is log 10 K value is minus 2.8814. And again here you are assuming the reference temperature is 1 atmosphere. So then using the K expression, you can substitute K value as 10 power minus 2.8814. So we are converting from log to K. So we are taking the power to 10. So 10 power minus 2.8814, which is equal to your mole fraction of the product raised to power their coefficient divided by reactant raised to power their coefficient, the same expression. And being pressure is equal to P reference, so the additional term or the pressure terms will get cancelled out. So it basically becomes 1. So 1 raised to power anything is 1. So this is equal to, again substituting the corresponding mole fraction values. So you will get 1 minus x by x into root of 1 minus x by 6.76 minus x. So if you see here, the value is different from the previous problem. So this is because here we are considering nitrogen, there was no nitrogen. So here because of nitrogen, your mole fraction values are different. So now again similarly like the previous problem, you can solve for x. So the only unknown here is x. So solving for x, we will get that x is equal to 0.9788. So again we can go back in the previous table, and we can substitute x value to find out what all the number of moles of each of the component present. So x is we found out 0.9788. So CO2 is 0.9788, and then you have CO as 0.0212 kilomoles of carbon monoxide and 0.0106 kilomoles of oxygen and 1.88 kilomoles of nitrogen. So this will not vary nitrogen because inert, so it will have same. So we know each of the individual moles of each of the components. So now we need to find out, the next part of the question was, we have found out the composition of the products. The next is to find out the rate of heat removal from the reactor. So to find out the rate of heat removal, we have to now apply an energy balance. So we apply an energy balance across the reactor. So that is nothing but your reactant minus a product. So enthalpy of CO minus x moles of enthalpy, sorry, and air this will become 0 because this is at 298 Kelvin and 1 atmosphere. So at that point your enthalpy of air is 0. So formation enthalpy of oxygen and nitrogen is 0, and your delta H also will be 0 because that is your reference temperature. So this will be enthalpy of carbon monoxide minus so reactant minus product. So reactant is enthalpy of carbon monoxide minus you have x moles of CO2 plus 1 minus x moles of CO plus 1 minus x moles of by 2 moles of oxygen, so into enthalpy of oxygen plus 1.88 into enthalpy of nitrogen. So similarly you can find out the formation enthalpy and the sensible enthalpy which required, and from the table you can substitute the expression here, and you will find out that your heat removed per moles of the feed which is supplied is 8E.117 megajoules per kilomoles of CO. So this is the amount of heat which is removed from the reactor. So any questions in this? Okay. So moving to the next question, we have LPG, which is a mixture of 40% of propane, which is C3H8, and 60% of butane, which is C4H10 by volume. So again this is given by volume, so you can take it as mole, so it will be equivalent to mole. So it undergoes partial combustion, that is cracking, in a reactor operating steadily at 1 atmosphere with 75% theoretical air. So here your theoretical air is 75%, that is 75% of the stoichiometric air value which you require. So assuming the products to be an equilibrium mixture of carbon dioxide, carbon monoxide, water, hydrogen and nitrogen, which is inert, at 1800 Kelvin, determine the composition and the rate at which heat is removed from the reactor. Assume that the reactants enter at 298 Kelvin. The enthalpy of formation of propane and butane may be taken as minus 103847 kilojoule per kilomole and as minus 124733 kilojoule per kilomole respectively. So what basically they have said is, we have a mixture of propane and butane which is at 40 to 60% by volume. This mixture is undergoing combustion and is forming, it is reacting with 75% of theoretical air of theoretical air, that is 75% of stoichiometric air value. So now you are assuming that this reaction is forming an equilibrium with products CO2, CO, H2O, H2 and nitrogen. So we need to find out the composition and the rate at which heat is removed from the reactor. So to find out first the stoichiometric air, so we can find out how much air is used for reaction. So we will write first the complete combustion reaction. So you have 0.4 moles of C3H8. So as I told, because that is in volume fraction, you can it is equivalent to your mole fraction. So you have 40%, that is 0.4 by volume, so it is equal to 0.4 moles. 0.4 moles of propane and 0.6 moles of butane. It is reacting with air and to form CO2, H2O and nitrogen. So this is a complete combustion reaction. So now if you balance carbon, you will take 3 into 0.4 plus 0.6 into 4 gives you 3.6. So you will have 3.6 moles of carbon dioxide. And similarly, if you do an oxygen balance, so similarly you can, if you do in a hydrogen balance, you will get 4.6 moles of H2O. So similarly then oxygen you can find out, it will take 5.9 moles. So 5.9 moles of air is required. So air contains oxygen and nitrogen again. So this is what the reaction will look like. So 0.4 C3H8 plus 0.6 C4H10 plus 5.9 into oxygen plus 3.76 of nitrogen, which is air. This gives you 3.6 moles of carbon dioxide plus 4.6 moles of water plus 22.184, which is nothing but 5.9 into 3.76 moles of nitrogen. So now they said in the problem that the mixture reacts with 75% of theoretical air. So that means 0.75 into 5.9. So that is the amount of air which is used for reaction. And we assume that this reaction comes to equilibrium with x kilomoles of carbon dioxide. So if we see the product, they are saying that equilibrium mixture is of carbon dioxide, carbon monoxide, water, H2 and N2. So that is the products which will be there. So there is no fuel which is present at the product. So 0.75 into 22.184 nitrogen plus x kilomoles of carbon dioxide, which we assume, plus 3.6 minus x moles CO plus 5.25 minus x moles of water plus x minus 0.65 moles of hydrogen. So if you see this, we can create a table again to say how much moles are present. So initially there is no moles of carbon dioxide, carbon monoxide, hydrogen and water, and nitrogen is in 17.313%. So at equilibrium, if we see, if we assume x kilomoles of carbon dioxide, we have 3.6 minus x kilomoles of carbon monoxide and 5.25 minus x moles of water, x minus 0.65 moles kilomoles of hydrogen, and same 17.13 mole kilomoles of nitrogen, which is inert. So if we add this up, we'll find that we have 25.33 kilomoles. So so now we can find out mole fraction of each of the component. So we know individual moles, so divide by the total number of moles. So CO2 will be x divided by 25.33, and similarly for each of the component we can find out what is the mole fraction present. So again, if you add this up, and you will see it is coming out to be 1. So now, since the mole fraction of carbon dioxide alone is unknown, because only unknown is here is x, so everything is expressed in terms of x, we can select one equilibrium reaction is sufficient to solve the reaction to find out x. So we assume CO2 plus H2 will form CO plus H2O. So if you see, we have 4 component, so we have to write expression for this 4 component. So CO2 is reacting with H2 to form CO plus H2O. So if you take this reaction, and we find for 1800 Kelvin what is the equilibrium coefficient. So your K value will come out to be log 10 K value is equal to 0.5758. So from this you can find out the equilibrium coefficient K, which will be raised to 10 power 0.5758. So this again you express it in terms of your mole fractions. So here each of the coefficient is 1, so it is directly proportional to your product of the mole fractions of product divided by reactant mole fraction product. So you are substituting what the mole fraction which we found out in the expression, so which will get 3.6 minus x into 5.25 minus x divided by x into x minus 0.65. So again now this we have got an expression, so the only unknown here is x, so we can find out x from this. So we will find out that x will get as 1.70151. So when we solve this, we will get x as 1.70151. So now this says that your product contains 1.70151 kilomoles of carbon dioxide, and again substituting just in the moles table, we can find out each of the component moles. So 1.7015 kilomoles of carbon dioxide, 1.89849 kilomoles of carbon monoxide, 3.54849 kilomoles of water, and 1.05151 kilomoles of hydrogen, and again same moles of nitrogen, 17.13. So now we have found out the composition. The next is to find out the heat removed from the reactor. So again, the product minus reactant minus product. So reactant is 0.4 moles of propane plus 0.6 moles of butane, and you have air, so which will be 0 because it is 1 atmosphere and 298 Kelvin, and minus your product. So product, we know each of the moles of the component present. So moles of carbon dioxide into your enthalpy formation plus your delta H, and similarly your moles of carbon monoxide into corresponding enthalpy plus moles of water into multiplied by the enthalpy of water plus moles of hydrogen multiplied by enthalpy of hydrogen plus moles of nitrogen into corresponding enthalpy of nitrogen. So this we have to find it out at 1800 Kelvin. So when we substitute the values of the enthalpy of formation and enthalpy from the table, and we know the enthalpy of formation for butane and propane, which is given in the question as minus 103847 kilojoule per kilomole and minus 124733 kilojoule per kilomole for butane. So we can substitute that, and we can find out that the heat removed per kilomole of the fuel is 281940.43 kilojoules. So now we have found out that. We will move on to the next question. Any doubt in the previous problem? Okay. So the next question is, we have 1 kilomole of carbon monoxide, hydrogen and oxygen, each at 5 atmosphere, react to form an equilibrium mixture of carbon monoxide, carbon dioxide, water, hydrogen and oxygen at 2500 Kelvin. So determine the composition of the equilibrium mixture. So we have COH2 and O2, which is reacting to form equilibrium mixture of carbon monoxide, CO2, H2, O2 and water. So here there is no nitrogen. So this is similar to the previous problem, second problem which we saw, CO reacting, but we have additional hydrogen here. So we'll see how to solve this. So now, so if you see in this problem, we have two products, CO2 and H2O, which we need to find out. So if you see, individual component is carbon, oxygen, hydrogen. So we'll have one expression, but then we have to find out two unknowns. So if we assume that x kilomole of carbon monoxide is formed and v kilomoles of hydrogen is present at equilibrium, then when we do an component balance of carbon, oxygen and hydrogen, this is what which we get for the other components. So we will have x kilomoles of carbon monoxide, which we assume, then we will have 1 minus x kilomoles of carbon dioxide plus v moles of hydrogen. So then we will have 1 minus v moles of water, then oxygen will be x plus v minus 1 by 2 moles of oxygen. So now we know each of the moles of the equilibrium components. So we can again create a table like this. So carbon dioxide, initially there is no carbon dioxide, so 0. Your components are CO, which is 1, O2 1, hydrogen 1, and water will be 0. So at equilibrium, so we have already have the expression for the equilibrium reaction. So at equilibrium we will have 1 minus x kilomoles of carbon dioxide, x kilomoles of carbon monoxide, x plus v minus 1 by 2 kilomoles of oxygen, and v moles of hydrogen, and 1 minus v moles of water. So if we add all this, we will get x plus v plus 3 by 2. So that is the total number of moles present at equilibrium. So mole fraction, again we can find mole fraction. So we individual moles divided by the total moles. So we have carbon dioxide as 2 into 1 minus x divided by x plus v plus 3. So similarly we can find the other mole fraction values for each of the component. So now since we had two unknowns x and v, we need two expression to find out the values. So if you have x and v are two unknowns, so we need two expression to find out the values to solve. And so we express two equations. So CO2 is dissociating into form CO plus half O2, so that is one expression, and again water in equilibrium with hydrogen and oxygen. So this is another expression. So for these two expressions, we will find out the corresponding equilibrium coefficient values, K values, at 2500 Kelvin. So which is given in the problem, 2500 Kelvin. So you are locked in K1. K1 is the equilibrium coefficient, the first reaction, CO2 in equilibrium with carbon monoxide and oxygen. So for that at 2500 Kelvin is minus 1.4338, and similarly for water in equilibrium with hydrogen and oxygen, your equilibrium coefficient is minus 2.2253. So if you write the equilibrium coefficient expression, so for first reaction is 10 power minus 1.4338, which is the K value, equals to y CO into y oxygen O2 raised to power half, because the coefficient is half, divided by the mole fraction of CO2 into P by P reference raised to power your product minus reactant. So your P here is 5 atmosphere, and your reference will be 1 atmosphere. So 5 by 1 raised to power. So if you see summation of coefficient of products is 1 plus half. So 1 plus half is 3 by 2 minus your reactant is 1. So 3 by 2 minus 1 is again half. So 5 raised to power half. This is what you get. So your ultimately your expression will be 10 power minus 1.4338 equals to root 5 into x by 1 minus x into root of x plus v minus 1 divided by x plus v plus 3. So this is what you get. And if you similarly for the second expression is K value is 10 raised to power minus 2.2253. So this is again your mole fraction of product divided by your reactant into again P by P reference raised to power the same. So since the same coefficients you have there, so you will get this expression similarly. So substituting the hydrogen, oxygen and water mole fractions which we found out. So substituting that, we will find out your expression as root 5 v by 1 minus v into root of x plus v minus 1 into x plus v plus 3. So now we have two expressions. So we can solve this two expression to find out x and v. So when we solve this, we will get x as 0.713343 and v is 0.286832. So this says that the equilibrium mixture contains 0.713343 kilomoles of carbon monoxide, 0.286832 kilomoles of hydrogen, and 0.286657 kilomoles of carbon dioxide, and 0.713168 kilomoles of water, and 8.75 into 10 power minus 2 kilomoles of oxygen. So that's what was asked, to find out the composition. So we have found out the composition of each of the component at equilibrium. So the only difference between the previous problem is we could solve using only one expression. So if you see here, so we have to assume just x kilomoles of CO2, and we could have find out all the coefficient for all of the other component. But here we had to assume two unknowns, so x and v, to find out each of the component moles. So any doubt in this problem? Okay. So moving on, we have a liquid N-dodecane, which is C12H26 at 298 Kelvin and air at 700 Kelvin steadily enter the combustor of a gas turbine engine. If the products form an equilibrium mixture of carbon dioxide, carbon monoxide, water, H2, O2, nitrogen and NO at 20 atmosphere, determine the composition of the mixture. If the temperature of the product is product is 700 Kelvin and 2200 Kelvin. So if you see this problem we solved in the previous week, doing a balance for a dodecane, and we found out what is the theoretical value of air which is used and so on. So here we solve the same problem for an equilibrium mixture, and similarly at same temperature of 700 Kelvin and 2200 Kelvin. So we will see how to proceed with this. So if you see, there are 7 different species in this product, so which is CO2, CO, H2O, H2, O2, nitrogen and NO. If you see, there are 7 species and 4 different atoms. So C, H, O, N. So we have 4 atoms. So we can get 4 component balances. So to get all the unknowns, we have to assume at least 3 unknowns. So that will assume x, mu and v. So we assume x for CO2, mu for water and N2 for nitrogen. So this we can use the same expression for previously also. So if I'll go back to the previous expression, see. So here you had CO, CO2, H2, H2O and O2. So you have 5 and you have 3 unknowns, 3 components. So C, H2, hydrogen and oxygen are 3 species which you have present, and you have 5 components which are present at equilibrium. So 5 minus 3 is 2. So you assume 2 unknowns to solve the problem. So similarly in this problem we have 7 unknowns and you have 4 species. So you can do 4 component balances to find that will give you 4 expressions, right? For solving the whole composition you need 7 components, so you have 7 expression to solve. So 4 expression you are getting it from the component balances. So C, H and O and N. So you need to assume 3 unknowns to solve, proceed further. So for that, now you are assuming dodecane 1 kilomoles of liquid dodecane, so C12H26 is reacting with 18.5. So this is from the previous week. We found out that 18.5 is the stoichiometric value of air. So 18.5 into is reacting with an excess amount of air. So 1 plus x into 18.5. So stoichiometric value is 18.5, and it is reacting with more than a stoichiometric value. So it is 1 plus x into 18.5 into air O2 plus 3.76 of nitrogen is reacting to form x kilomoles of carbon dioxide, 12 minus x kilomoles of carbon monoxide plus mu into H2O plus 13 minus mu H2 plus nu into N2 plus 2 into same balancing that 69.56 1 plus x minus V NO, and similarly for oxygen. So just like previously, we can find out the individual mole fractions for each of the component. So this is what you get for the mole fraction for each of the component. So now since we have 3 unknowns, so we need to have 3 equations. So these are the 3 expressions which will reaction which will consider to find out the 3 unknowns. So CO2 in equilibrium with CO plus half O2. So because we have CO2, H2 and N2, we will take individual components to for the reaction. So yeah, first CO2, so CO plus O2, half O2, then H2O, H2O in equilibrium with hydrogen and oxygen, then nitrogen, so half O2 plus half nitrogen, it reacts to form NO. So just like you can find out for 3 expressions the corresponding equilibrium coefficient at 1700 and 2200 Kelvin. So general expression will be K1 equals your same mole fraction of the products raised to power their coefficient divided by your reactant mole fraction into your P by P reference raised to power difference in coefficient of product minus reactants. So this is what you will get. So K1 is for the first expression YCO into YO2 divided by YCO2 into your P is 20 atmosphere and P reference 1, so 20 by 1 raised to power half, and similarly for the second reaction and for the third reaction. So and when you substitute the mole fraction of each of the components here, so this is what we get for K1, K2 and K3. So now we have 3 unknowns and 3 expressions. So the solution to the system of equation will be, so when we solve when we assumed the non-equilibrium case, so in the previous week the expression we found out that at 1700 you have nitrogen 157.866 kilomole and oxygen is 23.4858, and at 2200 Kelvin correspondingly 97.6066 and 7.4592. So in this example you will have when you solve this you will have the corresponding mole fractions as CO2 is 11.99 and H2 is 13 and same amount of nitrogen, and oxygen is 23.23. CO if you see is 10 power minus 3 and nitrogen oxide is forming as 0.51284. So when you increase the temperature, if you see additional amount of CO2 is decomposing into form CO and hydrogen, and your NO is also mole fractions are increasing. So when your temperature increasing, the other components mole fractions are also increasing. So you can see the difference. So if you temperature is increasing, the other component also will start increasing. So any question in this? So just like the previous problem, instead of their 2 component, now this is somewhat more tedious with the 3 component, but the procedure still remains the same. So any question in this? Okay. So the next question is hydrogen is burnt with 150% theoretical air in an adiabatic combustor operating at 1 atmosphere pressure. One more, see, if you have here x value, which is the theoretical, you have to use the same value in the previous problem, previous week problem which you get. So you can substitute that x value here. Okay. So next question is hydrogen is burnt with 150% theoretical air in an adiabatic combustor operating at 1 atmosphere pressure, assuming steady state operation and the reactant temperature to be 298 Kelvin. Determine the product temperature. Determine the equilibrium flame temperature, assuming the products to be an equilibrium mixture of water, hydrogen, oxygen, nitrogen, which is in it. So again, if you see, it is reacting with 150% of theoretical air. So first we need to find out what is the component of theoretical air which is present. And we need to find out both equilibrium flame temperature and the adiabatic flame temperature, and compare with how is the difference. So first we need to find out determine the product temperature and then compare it with the equilibrium flame temperature. So to find out the product temperature, so it is reacting with 150% of air, so hydrogen plus 1.5 into half into, so this expression, so which will give you H2O plus 0.25 oxygen plus 0.75 to 3.7576 nitrogen. So when we apply steady flow energy equation, so this is what we get, and the product temperature will be the adiabatic flame temperature. So assuming there is no heat rejected from the reactor, so Q is 0, and then your product minus reactant minus product, so H2 and delta H2 is by 0, and air will also be 0, so plus corresponding moles into your so 0.25 into oxygen, sorry, this is not 1.25, so minus 0.75 into oxygen, so minus delta H of the product, so water plus 0.25 into oxygen plus 0.75 into 3.76 into nitrogen. So substituting the enthalpy values of formation and the enthalpy at temperature which we have to find. So this is the expression which we will get. So delta H2O plus 0.25 delta HO2 plus 2.82 delta HN2 equals 241,830. So this substituting the formation enthalpy of water. So now we can assume some initial guess value to find out the temperature. So I assuming it is 2000. So corresponding to 2000, when you substitute the delta H values of each of the component, we'll find out it is 245,870. So this is higher than the actual value. So we reduce the temperature. So temperature is 1900. So for 1900 is 229711. So which is less than the actual value. So this should lie between 2000 and 1900. So when we interpolate it, we'll find out that the temperature of the product is 1975 Kelvin. So this is the adiabatic flame temperature or the product temperature. So now if you assume that the product is in equilibrium with the equilibrium component being water, H2, O2 and nitrogen. So again, if you see, there are 4 component and we have 3 species. So we have we can assume only one unknown. So we assume x moles of x kilomoles of water. So this gives you an expression of x moles of water plus 1 minus x kilomoles of hydrogen plus 1 minus 5 minus x by 2 of oxygen plus 0.75 into 3.76 of nitrogen. So again similarly, if you create a table, initially we have 1 mole of hydrogen and 0.75 moles of oxygen and 2.82 kilomoles of nitrogen, and at equilibrium we have 1 minus x kilomoles of hydrogen, 1 minus 5 minus x divided by 2 kilomoles of oxygen, x kilomoles of water, and 2.82 kilomoles of nitrogen. When we add up, we have total moles of 9.14 minus x divided by 2. So using this we can find out the individual mole fractions, and when that we sum it up, it will get 1. So since we have one unknown, we can assume this expression chemical equilibrium of water with hydrogen and oxygen, and for this if we write the corresponding equilibrium coefficient value, we will get Ks YH2 YO2 raised to power half divided by YH2O. Your P reference is 1 atmosphere and P is also 1 atmosphere here, so it will be 1. So when you substitute the mole fraction values here, so it will give it 1 minus x by x into root of 1.5 minus x by 9.14 minus x. So this is one expression. So since in this problem we don't know the x value, and we also don't know what is the temperature, equilibrium temperature, to find out the composition. So in the previous problems which we saw, we know what was the temperature of at equilibrium, so we assumed that temperature and corresponding K value we got from the table. But here we don't know the temperature, so we have two unknowns. So we have temperature and x value to find out the composition. So the second expression is we will write an energy balance. So we assume that there is no rejection from the reactor, so Q is 0, and when we write a similar expression, we will get one more equation, which is 0 equals x into minus 241830 plus delta H2O plus 1 minus x into delta H2 plus 1 minus 1.5 minus x by 2 delta HO2 plus 2.82 into delta HN2. So now we have two equations, and we have two unknowns, which is x and t. So now we have to find it, so just like the previous adiabatic flame temperature, we have to find this again iteratively. So starting guess value is 1900, because previously we saw it is 1975, and so we can start with 1900. So 1900 and x value is 0.9. We get the equilibrium flame temperature. So similarly, doing that iteratively and seeing whether this is getting satisfied. So assuming 1900, we will find out the K value for H2O and so on, and find out x value, and we will substitute the second expression, the x value and the delta H values of the corresponding component, and we will see that is coming out to be 0. If not, we have take a higher value or lower value corresponding to the value which we get. So doing that multiple times iteratively, we will get to that final equilibrium temperature is 1973 Kelvin, and x is 0.99902. So if we see here equilibrium temperature is 1973, and previously the problem we got 1975, so which is close. So this is happening because the equilibrium constant temperature is very small. So that's why your temperatures are close. If your equilibrium constant temperature is different, then they will see the difference in this temperature also. Any question in the previous problem? Okay. So next question is, determine the equilibrium flame temperature for the previous problem, assuming the products to be an equilibrium mixture of water, H2, O2, N2 and NO. So previously we said nitrogen is inert, now we are saying that nitrogen is not inert, it is also participating in the reaction and it is forming NO. So again, if you see, we have 3 atoms and 5 unknowns, so we have to assume 2 unknowns. So we assume x kilomoles of water and mu kilomoles of nitrogen, and we write an expression for that. So this is what we get, and you have 1.5% theoretical error. So 1.5 into your theoretical error is half kilomoles. So this is what we get: x kilomoles of water plus 1 minus x kilomoles of hydrogen plus mu moles of nitrogen plus 2 into 2.82 minus mu moles of NO plus 2 mu minus x minus 4.14 divided by 2 moles of oxygen. So we similarly create a table this, and we can find out the total moles, and from there we can find out the mole fractions. So since we have 2 unknowns, we write 2 expressions. H2O plus gives H2 plus half O2, and half O2 half N2 gives NO. So similarly we will write K1 and K2 values for the 2 expressions and substituting the mole fractions of each of the components. So this is 2 values. So in this case again we need to find out the equilibrium mixture and the flame temperature. We have to find the flame temperature. So we don't know the temperature and we have 2 unknowns, x mu. So total we have 3 unknowns. So another for temperature we will write a steady flow energy equation just like the previous problem. So when we write the expression, we will get x into minus 241830 plus delta H H2O plus 1 minus x delta H2, same oxygen moles into delta HO2 plus mu delta HN2 plus the moles of nitrogen oxide. So similarly like previous problem, since it is same, can start with the same equilibrium temperature value of 1973 and x and mu value, starting values. So assuming that and substituting the previous substituting in the expression and solving it iteratively. So just like previously we assume so assume 1973. So from there we estimate K1 and K2. So and solve for x and mu, and after solving for x and mu, we again substitute the x and mu value in this third expression, and for corresponding temperature we substitute the delta H values, and we see if that is equal to 0, and again proceed iteratively, and at the end we will find out your temperature is 1964 Kelvin and x is 0.9991 and mu is 2.8125. So this says that equilibrium product mixture composition is: water is 0.9991 kilomoles, hydrogen is 9 into 10 power minus 4 kilomole, nitrogen is 2.8125 kilomole, NO is 0.015 kilomole, and oxygen is 0.24295 kilomoles. So if you see, the equilibrium flame temperature is less than the adiabatic flame temperature because some amount of energy is went into dissociating water and the nitrogen oxide. So that's less temperature is because this is corresponding to your internal energy, right? So if the temperature is less, the energy is less because that energy is used somewhere else. So that energy is going in dissociating this component of water and nitrogen to form nitrogen oxide. So that's why your temperature here is less. So your flame temperature is 1965, and we saw when equilibrium is existing, your temperature is 1973, and now when you say that nitrogen is also participating in the reaction, it's not inert, it has dropped to 1964. Any questions? Okay. So the next question is: a closed system at a temperature of 20 degrees Celsius and a pressure of 1 atmosphere consists of a pure liquid water phase in equilibrium with a vapor phase composed of water vapor and dry air. So we have a closed system, so that is a closed container which is at a temperature of 20 degrees Celsius and 1 atmosphere. It is containing pure liquid water which is in equilibrium with uh, water vapor and air. So determine the temperature departure in percent of the partial pressure of water vapor from the saturation pressure of water at 20 degrees Celsius. So we'll see how to solve this. So for phase equilibrium to exist, that says that your chemical potential should be equal. So as I told in the previous start of the lecture, so your chemical potential of each of the components will be equal for the phase equilibrium to exist. So the chemical potential of water will be equal to the chemical potential of the water vapor. So I can say the component chemical potential is equal to the in both the phases. So your mu1 is the chemical potential in liquid and mu v is the chemical potential in as a vapor. So your mu1 is your dou g by dou ni, or the specific Gibbs energy at temperature T and P, and at vapor phase is G into T into PV, that is vapor pressure or the partial pressure of water vapor in the mixture of air and water vapor. So mu1 is equals to mu v, so that says your G equals to of the water vapor equals to G of liquid water. So your Gibbs energy, you can write it as H minus Ts. So you are expressing G as H and T is. So from this we know H of your temperature of water vapor is close to your enthalpy of the gaseous phase or enthalpy of vapor. So Hg, and similarly STPV is your entropy at G saturated vapor minus R ln PV by Psat. So and enthalpy of water is nothing but enthalpy of your water HF saturated liquid plus V into your difference in pressure P minus Psat. So and similarly your entropy of liquid is equals to entropy of your liquid SF. So you can find out SF, Hg, Sg and HF from the steam table, and Psat also can find out for 20 degrees Celsius. So this is the final expression which you get. So Hg minus T into Sg minus R ln PV by Psat equals HF plus Vf P minus Psat minus T into SF. So here if you see, the only unknown is PV. So if you write everything in terms of RT ln PV by Psat, you will get Vf into P minus Psat minus Hg minus HF minus T into Sg minus SF. So if you see this underlined expression, it's nothing but Sg minus SF is you can express it as Hg minus HF by T. So your entropy of phase change, Hg minus SF is the entropy during phase change. That is nothing but it happens at constant temperature. This being a pure fluid, it happens at constant temperature, and you can find out in entropy change at constant temperature as your heat supplied by temperature, and heat is nothing but your latent heat, which is Hg minus HF. So this underlying expression becomes 0. So your RT ln PV by Psat is equals to V into P minus Psat. So we know Psat, we know P. So the final expression is PV by Psat equals exponential Vf P minus Psat by RT. So at 20 degrees Celsius, from steam table we can find that Vf as 1.0018 into 10 power minus 3 and Psat at 0.0239 bar. So substituting that in the expression, we have Vf P minus P set by RTS 7.23 into 10 power minus 4. So, and R you can find for water is 8.314 divided by 18 kilonewton per kg Kelvin. So, substituting that we will get 7.23 into 10 power minus 4. So, substituting in the expression we will find out PV by Psat as 1.0072. So, your vapor pressure now is 1.00072 times Psat. So, if you find it in terms of percentage, which is nothing but PV minus Psat by Psat. So, PV by Psat minus 1 into 100 is what you have to do. So, we will get that change in percentage or the departure from the saturation pressure is 0.072%. So, I think I finished with the problems which I have prepared. If you have any doubts, you can ask. So, this is a phase equilibrium problem. I'll go through this problem again. So, this problem said that you have a closed system, you have water in equilibrium with a moist air. So, we said that any for phase equilibrium to happen, your chemical potential of the component in each of the phases should be equal. So, we know temperature and we know the pressure. So, we equated the chemical potential of each of the component, the water in both phases, and we said expressed that G specific Gibbs energy in terms of enthalpy and entropy H minus Ts. So, Gibbs energy is nothing but enthalpy minus temperature into entropy. So, we expressed in terms of that, and we expanded each of the terms. So, enthalpy at vapor phase is equal to enthalpy Hg, saturated gas, saturated vapor enthalpy, minus T into saturated entropy of vapor is saturated entropy minus R into ln PV by Psat, and then enthalpy of liquid is enthalpy of saturated liquid plus because of the pressure difference. So, V into delta P, and then again entropy of liquid will be the saturated liquid entropy. So, we equated that and we found out that enthalpy and entropy terms were getting cancelled out. So, the only unknown was PV. So, substituting for 20 degrees Celsius we found out the vapor pressure. So, and expression PV by Psat, and from there we found out what is the percentage difference between PV and Psat, and it came out to be 0.072%. Say any if you have any other doubt you can ask. And if you don't have any class, then if you don't have any doubts, you can end the session. Tomorrow we will have a review session where I'll go through the concepts of what is taught over the course. So, the major points I'll cover, I'll try to cover all that, and tomorrow it will be at 5. So, I'll cover from the first week to what was taught till week 12. So, I try to go through most of the concepts which is covered in this week. So, if you have any doubts, you can ask. Okay, then if you don't have any doubts, you can end the session. Thank you for joining. Am I audible? Do you have any doubts? Even if you have any doubts in the previous weeks, you can ask. Okay, then I'll end the session. Thanks for joining. Uh, Tomorrow I'll be taking a review class at 5, so please do join. I'll go over the concepts covered in thermodynamics course. Thank you.